Hello, everyone. My name is Paweł Wargocki. I am the Associate Professor at the Technical University of Denmark and also a partner in the ALDREN Project, which is the Alliance for Deep Renovation in Buildings, which is the project that is supported by European Commission. This is a training session on the topic that has been addressed by ALDREN, and it's called Addressing Health and Well-Being. Together with me, there will be three other speakers from CSTB in France, and CSTB is the convener of the entire project. And this will be Corinne Mandan, Rukshala Anton, and Wenjuan Wei. Well, let's get going. Our training session will contain a number of parts. Next slide, please. And this slide is showing the content of our training session. So in the first part, we will introduce the index that is being developed by the project to rate indoor environmental quality. And we will talk about the reason why it was developed and the concept of the entire index. Then in the second part, we will be talking about how to perform the measurements with the tail index. And then there will be examples for the measurements that were performed in part 3, and also the analysis of the results of the measurements and how to determine the tail index will be provided in part 4. Final part, which is a summary part, we will wrap up the entire session and give the view for the future of tail. Part 1 will be introduced by me, and also part 5, part 2 by Corinne Mandan, part 3 by Rukshala Anton, and part 4 by Wenjuan Wei. Let's get going with the background. So why we are even thinking about the measuring of indoor environmental quality when we are performing energy renovations. I think the energy renovations at the moment, they focus basically on energy. And because there is a very low rate of the energy renovations, and the reasons, there could be several reasons for them, there is a need for additional incentive to perform those energy renovations. These are crucial because in order to convert our economy into a green economy, the number of the renovations need to be much higher than it is at present. So one of the elements of different tools that can incentivize the and provide rational justification for performing deep energy renovation is to include the renovation or measurements of indoor environmental quality when performing deep energy renovations. And one of the reasons for that is that indoor environmental quality, when it is rated, we can be then later used to perform some economic calculations of the additional benefits that are not related to benefits that are obtained when the energy renovation is performed, because the energy use is reduced. So there is certainly a need for inclusion of indoor environmental quality measurements in the scope of deep energy renovation. And here we provide 4 arguments for that. First argument is, of course, that if the deep energy renovation is leading to aggravation of indoor environmental quality, this is the condition that we would like to avoid. So we need to somehow document that the indoor environmental quality is not reduced during this process. Not only this, we can also provide information whether and document that maybe indoor environmental quality is improved during the process of renovation. And so that could be also another important argument that deep energy renovation actually provides improvements to indoor environmental quality. The third is that if there is any changes to indoor environmental quality, I mean here improvements of indoor environmental quality, those perhaps can be converted into some economic value or economic benefit. If there are improvements that lead to reduction in health problems, reduction in absenteeism, or improved performance, those can be converted into the money gain, which is an additional benefit to the benefit that is obtained from the reduced energy use. But finally, and maybe central to all those three arguments that are provided above, is that EPBD mandate requires now that, or EPBD requires that indoor environmental quality is included as a part of deep energy renovation. It is actually included in the directive, and this is a part of the directive that actually refers to this element. So this is Article 2A on long-term renovation strategy, and point 1 is each member state shall establish a long-term renovation strategy. And the last sentence, it is said that each long-term renovation strategy shall be submitted in accordance with the applicable planning and reporting obligations, and shall encompass, and there are several elements, and one of the elements or articles, it's an Article 1G, it says an evidence-based estimate of expected energy savings and wider benefits such as those related to health, safety, and air quality. In other words, it is the formulation in the amendment to the directive, EPBD directive, that a part of the energy renovation process should document other benefits than only related to energy, and these are those related to health, safety, and air quality. Those benefits are associated with indoor environmental quality and also other aspects, but we are focusing here on indoor environmental quality. So how to measure indoor environmental quality in buildings? In order to propose a methodology to measure indoor environmental quality, one has to overview and see what are the currently applied methods for measuring of indoor environmental quality. And this is not a new topic, because such measurements have been performed for years, and there are different techniques and different parameters that are used to characterize the quality of indoor environmental quality. So one way to rate the indoor environmental quality would be to basically refer or reuse the existing methods that are used for measurements of indoor environmental quality. In order to identify those methods and see what the methods are used, the review of certification schemes and standards was performed in order to find out those methods that are in use, as well as the indicators that are proposed to characterize indoor environmental quality. And on this slide, you'll see the green building certification schemes that were reviewed, as well as standards that were reviewed, as well as projects which refer to this topic, and also research articles. Basically, the result of this review was that there is no common indicator of indoor environmental quality. Not only this, the different elements of indoor environmental quality, or components of indoor environmental quality, which is the thermal environment, indoor air quality, acoustic environment, and visual environment, are characterized by different indicators. And there are numerous indicators that are used in practice. For thermal environment, we have 19 indicators, for indoor air quality, 39, for acoustic environment, 20, visual environment, 12 indicators. And of course, There may be others that are not in use because of different reasons, but we don't know whether there will be any others that could be also used. So basically what we say from this review is that there are nearly 100 different indicators that are used to characterize indoor environmental quality and their components. And there is no any standard method for rating indoor environmental quality. We know how to do it, but we have not standardized it. We have not produced a metric or an index that can be used universally by in different projects or standards. Not only this, the different green building certification schemes, which have component of rating of indoor environmental quality, they also use different types of indicators to characterize indoor environmental quality. Not always, some of them they are matching and some of them are not. So in our project, the only way to advance that was to propose and suggest an index that can be associated with deep energy renovation and used to rate indoor environmental quality in a building prior to and after deep energy renovation. And we proposed the index, which is called TAIL. And also together with that index, we proposed the entire protocol and method on how this index can be used in connection with the measurements of IEQ in buildings during the energy renovation process that is taking place in a building. And later on, during this training session, you will learn how this index can be applied. But let's start first to introduce the index. The index is composed of the 4 letters, which is TAIL, which are nicely formed in a word tail. And the reason for that is not accidental, is because they contain or describe the 4 components of indoor environmental quality, which is a thermal environment for T, acoustic environment for A, indoor air quality for I, and luminous or light environment or visual environment for L. So the index that is shown on the right is composed of those 4 components, TAIL, just to show what is the quality of those components. But of course, what we are mostly interested in is the overall quality of indoor environment. This overall quality of indoor environment is presented in the middle of the index by the Roman number 1, 2, 3, 4, 1, 2, 3, 4. And how the Roman number and how the components and the colors behind the components are determined is shown in a moment, or will be discussed in a moment. So each component is described by the color, green, yellow, orange, and red, and the overall quality of indoor environment is described by the Roman numbers 1, 2, 3, 4. Yellow is the highest quality, and red is the lowest quality. 1 is the highest quality, and 4 is the lowest quality. In order to make a reference to existing standards, we used categorization of the quality of those components and of the entire indoor environmental quality that is used by the standard EN 16798-1. That is one of the standards that are supporting EPBD. So just to make connection to the EPBD and make also connection to the existing standards, we used those categorization. So there are 4 categories that are characterized or described or defined by this standard. And category 1 is the category with high level of expectation. Category 2 is normal level of expectation. For the indoor environmental quality, category 3 is a moderate level of expectation. And category 4 is low level of expectation. And those categories 1, 2, 3, 4 correspond to green, yellow, orange, and red. And they are applied for the components, TAIL, and for the overall indoor environmental quality. So this is the concept. So this is how it should be characterized, the indoor environmental quality and its components. But of course, behind each letter, there are a number of parameters that need to be measured and characterized in order to be able to tell whether the quality of that component is high or is low. So we need to define and select parameters that define those tail components. And these are the criteria based on which those parameters were selected. And of course, we have to bear in mind that we are talking about the energy renovation. So it's basically the process of energy renovation that is the one that is determining some of the decisions that are made here. So first is that these should be parameters that may be changed due to the process of deep energy renovation. It should be mentioned that the whole idea of deep energy renovation is not to deliberately change indoor environmental quality. The main starting point for the deep energy renovation is to reduce energy. However, this process may lead to changes in quality of indoor environment. Some parameters may be changed, control of temperature, building can be more tight, there may be a ventilation system installed, there could be some acoustic insulation made, there could be the different types of glazing used. All those actions can lead to changes of parameters or and then components characterizing quality of indoor environment. So what we did is we try to identify those parameters by reference to the projects which looked at this particular aspect. Then we selected parameters also that are included in existing building certification schemes and prescribed by the current standards. So one way would be to say, well, we could select the parameters that no one has used before. However, then it will be very difficult to make a connection with the existing methods used to characterize indoor environmental quality in buildings. And it would be very difficult to adopt or implement procedures that are developed by our project. Therefore, we have to be prudent here and we have to be pragmatic, I would say. So we decided that those parameters need to be the parameters that are already included in the standards. Also, because those standards define the ranges of those parameters that are then those ranges can be used to define the quality of indoor environment. Then another important parameter is that, or criteria, is that those parameters need to be measured, and there should be methods that are, how to say, available methods allowing the measurements. There should not be a very sophisticated and very expensive method for measurement of parameter that is included in tail, because then no one will characterize this parameter and no one will apply tail and no one will perform those measurements because of the cost or difficulty and so on and so on. So again, we need to be pragmatic here and basically use those parameters that can be measured. And then one of the, if you recall, one of the criteria for including reasons or justification for including the indoor environmental quality measurements in the renovation process is to estimate potential non-energy benefits associated with improvement of indoor environmental quality during renovation process. So the parameters that are selected to characterize tail or components of tail should also be parameters that have been shown for which the relationships to health, to performance and other parameters that can be economically quantified or from which the economic benefits can be calculated need to be made. It has been decided deliberately at that time that no subjective evaluations of the occupants of the buildings should be used to characterize components of tail. So no parameters that directly measure comfort, that could be subjective rating of the occupants, well-being, health, or productivity. Again, those were not considered to be included in that version of tail that we developed. These are the 12 parameters that were selected. And the list is pretty crude, but it can be implemented as it will be shown later. Actually, we can perform those measurements in buildings, and we can characterize quality of indoor environment in the buildings using those 12 parameters. So for the T component, which is a thermal environment, we used indoor temperature. And of course, the discussion can be, why not including air velocity? Why not including the operative temperature, which are probably the most important in that context as well? And the answers could be very simple. I mean, indoor temperature and operative temperature in buildings that are renovated are very close to each other. And air velocity is not a very simple measurement that can be applied in many buildings. For the component A, that is characterizing acoustic environment, acoustic quality of the space, we use a noise level in dBA. It is a sound pressure level. And of course, the debate can be again whether this is a valid measurement. Yes, it is, because it is actually prescribed by the standards. And we understand that there are other parameters that also could be considered, such as reverberation time or speech transmission index and so on. Again, those parameters are not very well established in standards, and the methodology is sophisticated at that moment to that extent that they cannot be applied in buildings. Then we see numerous parameters for indoor air quality. It's a component I of tail index. Well, in this case, it is truly an issue because we don't have an indoor air quality index, and indoor air quality can be characterized by numerous parameters. So again, we need to be very pragmatic here and need to select the parameters that we consider will be or could be the best representing the quality of I. And these are the first two, CO2 and ventilation rate. These are the most commonly used and also included in many standards. So CO2 is the characterizing concentration of carbon dioxide, which is considered to be an index of air quality, but rather ventilation efficiency, and ventilation rate, which is considered to be connected with the indoor air quality. The higher ventilation rate and the indoor air quality is considered to be higher. But also we included several parameters which are on the WHO list as considered to be related to great risk for the occupants of buildings, including formaldehyde, benzene, PM2.5, radon. We also have a relative humidity, and that is connected with the risk of mold and also a visible mold included in this. For the final component, which is a component L, we have two parameters. One that is characterizing the level of light that is delivered into the space, and the other one is that is characterizing amount of daylight that is delivered to the space. And the reason why we have this separation is because there's a lot of discussion about the importance of daylight for our work and for our well-being and so on. So we consider that that is also an important factor, as well as that some of the renovations may change actually the luminance or visual conditions in the space by changing the glazing and the size of the windows. So again, here there could be other parameters that could be considered, but these are the ones that are fairly well described in the standards and the literature, and the measurements can be performed. For all the 12 parameters, the 10 can be measured, and how they can be measured, by which instruments, and so on. This will be described in part 2. And one of them is modeled, and it's daylight factor, and one is done by visual inspection, which is the visible mold. We also indicate that some of those parameters that are on the list can also be modeled by the simulation tools that are used to predict the energy use in the renovated buildings. That is another dimension of the tale for the future that I will not discuss here, but we just pointed out that some of those parameters can actually be modeled or predicted, how they will be, what will be their levels in the renovated. So the selected parameters are included in standard and environmental assessment frameworks and green building certifications. And here this slide is showing that 11 of those is included in EN standard that was mentioned earlier, and in levels, which is the sustainability tool developed by European Commission, in WELL, and then there are several of those in different certification schemes. So actually the criteria, including parameters that are well represented in other certification schemes, is fulfilled here, and also suggests that by calculating tail or by certifying some of the buildings using some certification schemes, the tail can be automatically determined. So each of the 12 parameters is assessed according to the 4 categories. So those categories were introduced before, and from their category level, the level of the quality of each component is determined. And how this is done will be presented in part 2 on the measuring protocol and overall concept, and this will be introduced by Corinne Mandin.
Good morning or good afternoon. My name is Corinne Mandin. I'm working at the Scientific and Technical Center for Building, the CSTB, in France. And I will present you a few elements about the measuring protocol to characterize the tail index. Next slide, please. So tail is determined before and after a renovation to characterize the influence on indoor environment quality of this renovation. We recommend to perform the measurement at the same season before and after to avoid any difficulty to interpret your result. Ideally, it's best to do 2 seasons before and 2 seasons after the renovation. And the last important information is that during your on-site measurement, the building should be absolutely operated and occupied as usual to capture the typical condition. You must avoid any specific situation, and if there is a specific event planned in the building, you need to postpone your measurement campaign. Next, please. So a few elements about the number of sampling locations. Of course, the building can be very large, so you cannot do measurement in all the rooms. So the number of sampling location is a compromise between capturing the representativeness of the sampling location for the whole building and also the technical and economic feasibility. Technical because maybe you don't have the devices and equipment to instrument many rooms, and also economically we cannot measure everywhere. So we recommend to measure between 2 and 10 rooms in the building, whatever the size. But check that if you have 10 rooms, that these 10 rooms represent at least 10% of the occupied area. It means the office floor area for offices and the guest room floor area for hotels. Regarding the choice of the sampling location, so since we have a limited number of measuring locations, we recommend not to measure in rooms that are not occupied permanently. So avoid the lobby in hotels, avoid the meeting rooms in office building. Do the measurement in offices, in workplace, in office building, and in rooms in hotels. And to choose this different location, you must keep in mind that you must have diversity in the rooms. So it means you have to choose, you have to basically decide to measure at the lowest occupied level and at the highest, and then you choose intermediate levels. Choose different orientations, because we know that depending the orientation on the street or on the garden, you have a different influence of light or noise or air pollution. So please pay attention to have different orientation of your rooms. Choose also different types of indoor spaces. It means different indoor materials, different ventilation system, if you have different type of spaces in the building. If you have single offices and open plan offices, be sure that you have a mixed type of rooms in your sample. And once again, the rooms you choose must be normally occupied during the measurement. So avoid any rooms that would be empty during the measurement. Regarding the duration of the sampling, so it depends on the parameter. It's at least 1 month for temperature and relative humidity to have a long-term measurements. For radon must only be measured in buildings that are located in radon-prone area. Or if you have such a building, the measurement must be done during 2 months. And for the other parameter, this is 1 week, from Monday to Friday in an office building. And in an hotel, it's from Monday to Monday, Tuesday to Tuesday, or Wednesday to Wednesday, etc. So keep in mind a few things. It's always better to visit the building before the measurement, to choose the different sampling location, to discuss with the building owners, and if possible, take pictures to remember the places you have chosen, and also to remember when you will interpret the results, the rooms, if you need. Before going on site, also collect practical information, the access to the buildings, if there is a car park or if you need to be on the streets. Ask for a plan to clearly mention the selected measuring location. And when you are on site, also during the measuring week, collect as many technical information as you can. The type of ventilation system, the type of heating system. Record if you sample small offices or open plan offices, because you need this information for the calculation of tail. Ask if there was any special event recently, a fire in the building, new furniture introduced in the building, new floorings, because this has a strong influence on indoor air quality or also on acoustic. So you must have this information to correctly interpret your result. Ask also if there was a water damage. This can influence the presence of mold. And during the sampling week, when you will collect the equipment, the last day, ask if there was any special event during the sampling. Problem with the heating system, this is important to interpret the temperature measurement. Problem with the ventilation system, if it was turned off for a while, you need to know this information to correctly characterize tail when you will interpret the results. So now I leave the floor to Rukshala Anton to introduce more in details the measurement and the equipment.
Next slide, please. Okay. Good morning, everyone. My name is Rukshala Anton, and I work in Corinne's team with Wenjuan. I'm a research engineer. So I'm going to describe the sensors that we used during a pilot. So for the temperature sensor, you have here in the picture the temperature sensor, sorry. The acoustic environment is measured by a sonometer, and the indoor air quality are we use different sensors, and we have a mold observation for the mold contamination and radon measurement if there is a risk area. And we have also light measurement. This measurement should be ideally performed in the center of the room, not closer than 1 meter to the wall, and about 0.8 to 1 meter over the floor or on a table, desk, or the bedside table in hotels, for example, in order to have the indoor quality that we breathe. These sensors will be put on a rack, and you need to stay away from heating sources, and you need to put them not into direct sun and avoid ventilation channels. So here is the description of the temperature sensors. We will need calibrated sensors with an accuracy of at least 0.5 degrees Celsius. The logging interval is from 1 to 10 minutes. And additionally, we can measure outdoor temperature, or it can be obtained from the nearby meteorological station. These measurements should be performed recommended to use 1 to 10 minute interval. We will have unoccupied building, but with all systems in operation. And in order to have typical levels of background ambient noise, we will perform these measurements during working hours in office buildings and during the night in hotels. Next slide, please. This is the description of measuring equipment for the indoor air quality. Except for mold, which shall be quantified by observation, we will assess the contaminated surfaces. All parameters defining indoor air quality in the tail index shall be measured. As you can see in the picture on the left, we have passive samplers for chemical pollution. The blue one is for the formaldehyde, and the yellow one is for the benzene, and it should be suspended on the rack, and we shouldn't use any adhesive. We have time integrated measurement, which are made 24 hours during 5 days or 7 days, according if it's hotels or offices. We will have gravimetric measurements, the particle matter measurements. You have the green one, which is used. Then we have the CO2 measurements, and as well as radon if need in the risk area. And we will have spot measurements of ventilation rates. These measurements should be performed during working hours and nights in hotel rooms when occupied. The measurements of light will be done with a lux meter. We will measure illuminance. This refers to the total light delivered on a surface by either an especially installed system or through windows daylight at the same time. We will use calibrated sensors that have the accuracy of at least plus or minus 3 lux. We will perform spot measurement, or we can make also continuous measurements. In case of logging, we will recommend to use 1 to 10 minutes of logging interval. These measurements shall be repeated at least 2 days and 3 times per day in case of the spot measurement. As usual, we will make this light measurement during working hours in office building and during night in hotels. Here you have an example for one ALDREN pilot. We instrumented 4 offices at 2 levels, 2 offices at the ground floor and 2 offices at the first floor. The thermal environment has been measured during 1 month. the acoustic environment during 5 days as the CO2 and the chemical pollution and particle matters. The relative humidity has been measured 1 month as the temperature. And for the light environment in red, we did it 3 times, morning, midday, afternoon, the first day and the last day. Here you have some pictures of the deployment in a building. As you can see on the first picture, we have a rack on which we put the sonometer for the sound. You can see the diffusive body in yellow and blue for the chemical pollution. And in the picture in the middle, you can see the other side of the rack, and you can see the CO2 sensor. And on the last picture, you have the green sensor, which is for the particles. As you can see, the rack is put in the center of the room, and it's about 1 meter from the floor. For the light measurement, we will have 5 spots, 4 in each corner and 1 in the center of the building. And we will perform the measurement with window blind and without window blind, and with light and without light, for example, in hotels. My colleague Wenjuan Wei is going to show you the analysis of results from the measurement with examples from one pilot.
Hello, everyone. My name is Wenjuan Wei, and I also work at CSTB. I'll continue and talk about the analysis of the measurement results, taking the pilot building that was introduced earlier as an example. To calculate the tail index for building, we have developed a calculation tool, which is an Excel file as shown on the slide. At the bottom of the Excel file, we can see several spreadsheets highlighted in different colors. The spreadsheets are dedicated to the calculation of the tail indicators. The one highlighted in pink are for the thermal environment calculation. The ones highlighted in green are for the acoustic environment calculation. The ones highlighted in orange are for the indoor air quality calculation, and the ones highlighted in purple are for the luminous environment calculation. In each spreadsheet, the input data that need to be filled out by users are highlighted in blue. Once the blue cells are filled out, the tail index is calculated automatically. For example, the spreadsheet on this slide is for the thermal environment calculation, and the indicator is the indoor air temperature. The input data highlighted in blue are the temperature profiles in the measured rooms. The input data for calculating the tail index are the measured or modeled data of the tail indicators. They are indoor air temperature, which can be measured using online measurements for 1 month. Sound pressure level, which can be measured using online measurements for 1 week. CO2 concentration, which can be measured using online measurements for 1 week. Ventilation rate, measured at the first day and the last day of the measurement week. Relative humidity, using online measurements for 1 month. Visible mode, which is observed visually. Formaldehyde and benzene concentrations, using passive measurements for 1 week. Radon concentration, also using passive measurements. PM 2.5 concentration, using online measurements for 1 week. Daylight factor, which is modeled. And illuminance level, which can be measured at the first day and the last day of the measurement week in the morning, midday, and afternoon. Data during working hours in offices from 9 a.m. to 5 p.m. by default, and during night hours in hotels from 9 p.m. to 6 a.m. of the next day by default should be used for calculating the tail index. Measurements of the noise level should be performed in unoccupied spaces during working hours in offices. If the offices are occupied during the day, data between 6 to 8 a.m. and between 6 to 8 p.m. should be used for calculating the tail index. The output of the tail calculation tool is the results of the tail index as shown in the figure on the right side of the slide. The tail calculation tool calculates the quality levels of the thermal environment T, acoustic environment A, indoor air quality I, and luminous environment L, as well as the overall indoor environmental quality level of the building. I will show an example in the next few slides to explain how to explore the TEL calculation results. The building that is taken as the example is the pilot building introduced earlier. The measurement was performed during the heating season. After filling out the input data of the TEL indicators, as I mentioned in my previous slides, the overall IEQ level of the building is red, which is level 4 as shown in the circle in the middle of the squares in the figure. It indicates that the building has a large potential for IEQ improvement during renovation operations. The levels of the 4 TEL components, T, A, I, and L, shown as the squares around the circle are yellow, red, orange, and red respectively. They indicate the improvement potential of the thermal, acoustic, and luminous environments, as well as IEQ. The TEL calculation tool allows visualizing the quality level of the TEL indicators for each measured room. We will start from the TEL T thermal environment. Indoor air temperature is the only indicator for the thermal environment, and 4 rooms were measured in this building. The thermal environment levels of the 4 rooms are from green to orange. It suggests that indoor air temperature varied among different rooms during the heating season in the building at the current state. The indoor air temperature data in the 4 rooms show that the temperature varies not only among different rooms, but also from one day to another in each room. Therefore, the thermal comfort can be improved by reducing the indoor temperature variation during the working hours. The TEL A acoustic environment levels of the 4 rooms are all in red. It suggests that the acoustic environment of the building is poor at the current state. The sound pressure level is the only indicator for the acoustic environment, and it was often higher than 40 dBA in the measured rooms without occupation. The TEL A indoor air quality has several indicators: CO2, ventilation, air relative humidity, visible mold, benzene, formaldehyde, radon, and PM2.5. Most of them have green or yellow levels in the measured rooms. It suggests that the building has efficient ventilation and low concentrations of indoor pollutants. However, the TEL I level of the building is orange because the air relative humidity was often lower than 25% in the measured rooms during the heating season. It can cause dryness. The TEL L luminous environment has 2 indicators: daylight factor and illuminance level. Daylight factor was not assessed for this building because it is the only indicator that requires modeling, and this building is fully assessed based on measurements. According to the illuminance level, the luminous environment of the building is poor at the current state. It is because some rooms were over-illuminated and others were under-illuminated during the measurement period. And here goes the summary. Powell, please.
Thank you, Angela. And thank you, Ruxala and Corinne. And this is a time to wrap up the entire training session. And so far, we have learned why we need an index for rating of indoor environmental quality. We have introduced this index and how it is built, what components it includes, and what parameters it does include. Also, we have learned the protocol for how to perform the measurements. We saw the instrumentation and the analysis. In that short training session, we were not able to introduce very in details the ranges of parameters as well as the accuracy and precision of all the instrumentation. But we want to assure you that there is a protocol that has been developed, a very detailed protocol, and all these data have been carefully considered and included. And I will be wrapping up, and I realize that we haven't tell you one most important information, but I will do it probably when we will be wrapping up here now about this information. So next slide, please. TAIL, summarizing, the TAIL is a framework for rating of indoor environmental quality and its component. It can be used to develop other metrics compatible with TAIL. So because it contains elements that are included in different other parameters that are used in practice. It is a comparative index. Basically, the idea when we develop the index is to make a comparison before or prior to renovation and after renovation. And developed having in mind mainly offices and hotels. These are the buildings which were the major objective of the ALDREN project. So we're in the focus of ALDREN project. So once again, is a framework. It provides a methodology for measurements of indoor environmental quality, and as a comparative index comparing before and after. And TAIL integrates all IAQ components. So TAIL are the 4 components of indoor environmental quality, and all components are included. And the quality of those components is determined by mainly measurements. One parameter is observed and one parameter is modeled. Unlike the other credit systems or accreditation systems for the buildings, TAIL is not using the arbitrary credits. So to say, if you measure temperature of 23 or CO2 of 1000 ppm, there will be no credit given for this, which will be either 1, 2, or 3, or 4, or 5 credits. What is used to determine the quality is an actual measurement with the reference to existing standards and guidelines. So, because to be transparent, no arbitrary credits are given, and the guidelines and standards are developed based on the experiments and experimental work in which the actual measurements were related to the different quality levels. And this is the part that we forgot to introduce in the beginning, is that the TAIL treats all indoor environmental quality components equally. In other words, no weightings are applied for the components. So the overall quality of indoor environment will be the quality of the worst quality of the components of TAIL. So in the example that we see in the upper corner of this slide is that T is the high quality, A is the yellow, that is a second, and then quality, moderate quality, typical quality, moderate quality, and poor quality is I. And I, in this case, determine the quality, overall quality of the index, which is the category 4, the worst quality. Why we decided to do that? And there are 2 basically reasons for that. Is one reason is that we don't have good evidence and information on whether the weighting of the different components of indoor environmental quality can be made. So we don't know whether the overall quality, for the overall quality, all the components contribute equally. There could be that temperature contributes slightly more, maybe the light slightly more, or maybe acoustic environment slightly more. The second point is to create incentive, basically, to improve indoor environmental quality. In this case that is presented here, the average, if we weighted the average indoor environmental quality, would be probably level orange or level yellow, and or level 3 or 2. And in such a case, we would be overlooking one of the important components, which is I, which has a poor air quality. But if we indicate in the overall environmental quality that there is some issue with one of the components, that would create an incentive to improve that component and at the same time to improve the overall indoor environmental quality. We want to say here that the same approach is used with the ambient air quality measurements, in which the worst component is determining the level of the ambient air quality, and no weighting or averaging is made. And of course, that can be debated whether the approach is good or not, but in that particular version and the framework, we propose to use this approach. So once again, the overall quality is determined by the quality of the worst component of tail. And the tail complements the existing approaches for indoor air quality ratings, and of course addresses EPBD mandate and is compliant with major certification schemes, as we said. So yes, certainly tail needs validation, and such validation has been performed to some extent, and further validations need to be made. We also believe that tail with an additional extensions and amendments can be used for other types of buildings, not only offices and hotels, but also schools and homes. But of course, that has to be verified. So to wrap it up, this is a crude measurement, but probably one and the only one that currently exists to provide the overall assessment and rating of indoor environmental quality. We believe that by developing such an index, it is expected to increase the interest of investors in indoor environmental quality, but also in performing the energy renovations. So how do we see tail in the future? Can I have a next slide, please? So we believe that there are three levels of how the tail will be developed in a short time, which will be a validation of the current version of the tail with modifications to the measuring protocol, maybe ranges of indoor of the parameters underlying it. Particularly looking at the sensitivity of tail to detect the differences. That could be the second phase of the medium time frame, is the sensitivity to distinguish differences in indoor environmental quality across buildings, and also verification of the long-term measurements and also sophisticated measurements. So they're proposing fairly crude and simple method of measurements, and also measurements that are taken for a month, for a week, and at best in 2 seasons. And the question would be whether and how much that would deviate from the measurements that are performed over the entire year. In this way, one would be able to establish the potential precision and accuracy of the rating of indoor environmental quality. So this is basically the point, the medium time frame. We need to think about the precision and sensitivity, so all the aspects related to accuracy of determining the quality of indoor environment using tail. In, of course, long time frame, that can be considered to many aspects of development of tail. And to me, there are three most important elements of that is to extension to other types of buildings and also to existing buildings. So not using tail as the relative index, but also an absolute index. Also, the second point is to advance the measuring protocol, including more measurements and other measurements that would probably even better reflect the conditions in indoor environment. And the third point would be to be able to monetize tail and associate the benefit that is related with achieving a certain level of tail in the framework. Next slide. So that will be all. Before concluding and adjourning our session, I would like to say that we published some documents that describe the different indices that are used in the building certification schemes, and this is the paper on the left in energy and buildings, and then there is a short paper on the right in ASHRAE journal on the tail index. We are now very close to submission of the final paper describing tail protocol, tail measurements, and all those elements which are included in our training session today. And we hope that it's gonna be published in Energy and Buildings by the end of the year, or any other journal where this paper will be accepted. Next slide, please. So thank you very much for your attention. If you want to learn more about ALDREN project, please visit us at www.aldren.eu, where you also find the connection to each of the speakers of this training session. And then you can connect with us if you have further questions that are related to the methodology that was developed and presented during this training session. We thank you very much for your attention, and we hope that this session was fruitful and provided you with the information that you needed. And we hope that you, in the future, in all your projects, you will start to use the tail index. Thank you very much.